Jim Kunkel here. Make sure that you subscribe to my channel and set the notification bell to all so that you won't miss any of my new content. I'm Jim Kunkel and welcome to another episode of Global Topic. On today's episode, I'll be talking to Adnan Akman, who's a Master of Science University student at the Delft University of Technology in the Netherlands. We'll be talking about advanced high-strength steel and the corrosion protection of it. I hope you enjoy this episode. Adnan, welcome.
Hi, Jim. Thanks for having me.
Hey, if you could take a couple of minutes here and explain your background and what you're doing at the university.
Exactly. I'm a second-year master's student in Delft. I did my bachelor in the field of material science and engineering in Ankara, Turkey. And after that, I graduated July 2019. Then I started a master program in Delft University of Technology in September 2019 without giving a break. Then mainly I'm studying material science and engineering. My specialization is metal science and technology. And I'm enthusiastic to learn about steels, always stainless steels, advanced high-strength steels. And also I'm looking for, I'm searching most of the time the corrosion behavior of steels, how they act with different environments and how we can protect steels from corrosion.
Very good. You know, in relation to advanced high-strength steels, you know, many of those who are watching this episode will have, you know, limited or no knowledge about advanced high-strength steels. You know, what is this class of steels and what advantages and uses in the world do they have?
So, advanced high-strength steels are, especially steel is an important material for everyone. And if you consider, for example, a car, for example, is it possible to see aluminum alloys, magnesium alloys, and steel? So if you consider, for example, a car body frame, we are looking for, consider a part of the car, and we are looking for most of the time strength and stiffness at the same time. So structural applications also requires this, but if you want to increase the strength, most of the time we are looking for thick parts, thick components. So if you increase the thickness of your car, directly it will affect the weight of the car. So due to the increment in the weight, it will increase the fuel consumption and you will affect the environment with production of greenhouse gases. So we are looking for thin and lightweight parts in our car body frames. And also in addition to them, we are looking for steels easy to weld and easy to form to give a specific shape of the car. And also, we are looking for safe steels. I mean, passenger safety is the most important issue, and also affordability of the cars, another issue. And lastly, recyclability. I mean, steel is the most recyclable metal in the world. I mentioned about lots of requirements, I know, but to meet with the diverse requirements of today's vehicle, advanced high-strength steels are quite suitable. If you consider a car, it is possible to see aluminum alloys, magnesium alloys, even composites, and steels. But what about the classification of automotive steels? We can classify automotive steels into three groups. These are low-strength steels, high-strength steels, and advanced high-strength steels. Low-strength steels are mild steels or interstitial-free steels. They are basically single-phase steels. I mean, the microstructure of the steel is ferritic. I mean, ferrite is a phase from a steel, okay? It is the softest phase in steel. If you check high-strength steels, it is possible to see bicarbonate steels or high-strength low-alloy steels, and their microstructure also single-phase. I mean, most of the time ferritic, and it is possible to see some pearlitic structure in their microstructure. If you check these steels, their strength is not much suitable for specific application. And people discovered that advanced high-strength steels. Advanced high-strength steels are not like these steels. They exhibit high mechanical properties with their unique and complex microstructures. So if you consider advanced high-strength steels, they are sophisticated with their unique microstructure and with their special chemistries. So they are quite unique with high mechanical properties, especially high strength and ductility. But the complexity in the microstructure comes from thermomechanical processes, I mean cold rolling, hot rolling, and the heat treatment profile of the steels. So I would like to dive into classification of advanced high strength steels. We can classify these steels into three groups. These are first generation, second generation, and third generation. First generation steels are dual phase steels, transformation induced plastic steels, or martensite steels, for example. Second generation steels are mostly austenitic, for example, twinning induced plastic steels. And third generations, they are in still RD stage. I mean, engineers are still working on improvement of third generation advanced high strength steels. For example, quenching and partitioning is a quite important steel from third generation advanced high strength steel. For example, I would like to give small information about some specific groups, the most common groups for automotive industry. For example, dual phase steels. As you can understand from its name, it contains two phase, dual. These are ferrite matrix with martensite island. Martensite is the hardest phase in steel. So if you consider the microstructure, the combination of ferrite and martensite at the same time. But how we can achieve high strength and ductility? You can think basically, ferrite is responsible from ductility, martensite islands are responsible from strength. So by combining different microstructures, I mean kind of microstructural tailoring, you can achieve desired properties. In addition to dual phase steels, transformation induced plasticity steels, also called TLIP steels, are quite popular for automotive industry. As you can understand, there's a transformation. But what kind of transformation? If you check the microstructure of the TLIP steels, it is possible to see really complex microstructure, especially compared to dual phase steel. TLIP steels are quite complicated. They contain ferrite matrix with martensite, retainostenite, and bainite. So I mentioned transformation. What kind of transformation? Due to the deformation or forming, the retainostenite can transform into martensite. And with this transformation, local strength of the steel will increase. And due to this increment, work hardening rate, I mean formability of the steel, can increase easily. What about second generation advanced high strength steel? For example, I mentioned twinning induced plasticity, also called TWIP steels. So twinning is a mechanism to help to see, twin deformation twins by the help of a deformation in the microstructure. I mean, we are applying a deformation, kind of deformation. It can be a crash. With this deformation, it is possible to see deformation twins in their microstructure. With that deformation twins, the twin boundaries act as a grain boundary in the steel, and it will increase the strength of the steel. Normally, TWIP steels are fully austenitic steels. I mentioned about these advanced high strength steels are mostly complex steels, but this is fully austenitic steels. So how? Normally, austenite is a not stable phase at room temperature. So how we can stabilize them? Addition of elements. So their chemistry is different. Manganese, for example, in steel, especially in TWIP steel, used to stabilize austenite at room temperature. TWIP steels contains at least 17% of manganese. Due to this high content of manganese, these TWIP steels are a bit costly, and their forming and welding is a bit problem. So in addition to them, third generation advanced high strength steels are quite popular nowadays because of engineers are still working on it. The main aim of quenching and partitioning steels from third generation is to achieve high strength and high ductility at the same time, but with lower cost. So, for example, quenching and partitioning is a special heat treatment. I mentioned about from my first talk, for example, the chemistry and heat treatment profile is different compared to other steels. High strength steels or low strength steels. So I mentioned about lots of steel. Dual phase steels, TWIP steels, martensite steels. But what about an application in real life? So if you consider a car, in a crash zone, consider crash zones, for example, or in a high-speed crash, the front and back side of the car called crumple zones in the case of crash, and the middle side of the car called safety cage. Safety cage is the location actually where passenger compartments are located. We are carrying passengers. So in a case of crash, crumple zones has to absorb energy as much as possible to protect the passengers. So we are looking for high energy absorption metals with high strength and high ductility at the same time. For example, dual phase steels and triple steels are good at energy absorption and suitable for back and front crumple zones. If you consider, for example, safety cage, passenger compartments, we are looking for no deformation because of we are carrying passenger. So what kind of steels? Martenswick steels are suitable for safety cage, passenger compartments. Why? Martenswick is the hardest phase in steel. So with Martenswick steels, it is possible to achieve high strength with limited ductility at the same time. So for long story short, I can say different part of the car requires different steels due to the different properties. Crumple zones, maybe dual phase is suitable or trip steels are suitable, but in safety cage, for example, Martenswick steels are suitable.
That's amazing. I really appreciate the background on all that, and it's a lot of good things to know related to the different industries, but also looking at the aspect where you mentioned about the automotive industry as well, regarding safety and everything like that. So let me ask you this: the World Steel Association, they recommend the use of electrogalvanizing and hot dip galvanizing, or hot dip galvanneal. What's the basic advantages does the galvanizing provide to the high strength steel?
I see. It's a good question. Thank you for the question. So corrosion protection of advanced high strength steel is an important issue. Corrosion protection of metals is an important issue. If you consider metal structural applications, we can protect the structures with, for example, coatings, as you know, with metallic coatings or organic coatings, or some log structures or pipelines can be protected with cathodic protection ways, impressed current cathodic protection, or sacrificial cathodic protection. But the cathodic protection techniques will not work well for an automotive. So the most suitable way is for corrosion protection is metallic coatings. So galvanizing is a kind of metallic coating. So basically, I can say that formation of zinc layer on top of the steel. Why? Because of zinc will sacrifice itself to protect the steel. Zinc is anodic compared with steel, so it will sacrifice itself in a harsh environment, in a corrosive environment, and it will protect the steel. So we can classify the galvanizing technique into three groups, as we mentioned. These are hot dip galvanizing, electrogalvanizing, and galvannealing. Hot dip galvanizing is a quite popular technique nowadays, also in industry. We are dipping our steel component to a bed, zinc bed. The processing temperature is around 450 to 500 degrees Celsius. We are dipping our steel component into zinc bed. And for example, if there is a case for over zinc, for example, you can remove the zincs with air knives. And after some time, zinc will cool down on the surface. And you remove your steel, you have a zinc layer on top of your steel. It's an excellent way for corrosion protection of advanced high-strength steel. In addition to this technique, electrogalvanizing is a quite popular technique for zinc coatings. If you consider, for example, electrogalvanizing, the main difference is actually the idea is same, application of zinc coating, but in electrogalvanizing there is a case for usage of electricity. We are using current of electricity to form a zinc layer on top of our steel. You can think like that. You have a basic cell. You can think like an electrochemical cell. We have an electrolyte kind of media to ionic transfer, to zinc transfer through zinc to steel. We have an electrical current. We have a cathode, which is our steel. We have an anode, which is our zinc. So with the application of current, zinc will transfer through the steel surface, and you have a zinc layer on top of your steel. But if you want to compare these two techniques, for example, the processing temperature in electrogalvanizing is quite low compared to hot dip galvanizing. And also, the thickness in hot dip galvanizing, it is more thick compared to electrogalvanizing. For example, if you are looking for outdoor applications, okay, hot dip galvanizing is quite suitable due to the thick layer. In electrogalvanizing, the thickness is limited, thinner than hot dip galvanizing. And lastly, I can say that due to the thin layers, electrogalvanized layers looks better and smooth, aesthetically, compared to hot dip galvanizing. And last one is hot dip galvannealing, also called galvannealing. In galvannealing, the idea is same with hot dip galvanizing. I mean, the zinc pass through the zinc bed, your steel pass through the zinc bed, and I mean, you can think like a hot dip galvanizing. Addition with the induction heating system. So in induction heating system, your zinc coated steel pass through the induction system. It will liquefy, and there is an iron source close to induction system, and iron will diffuse into your layer. So your final coating is zinc iron alloy. Instead of pure zinc, in galvannealing, your coating is a zinc iron alloy. If you check the chemical composition of the coating, it is possible to see 9 to 12% bulk iron in your coating. But the aim of the coating is to increase formability and corrosion resistance of the steel, like previous techniques. But the problem in this technique, if you increase the zinc content, if you cannot control the zinc content, the formability of the steel will be quite hard.
I appreciate you running through the different processes related to galvanizing. Recent developments, reported by the Auto Steel Partnership are centered in producing lightweight, advanced high-strength steel that's inherent materials and production processes which provide for, longer-term corrosion resistance versus, the coating or the galvanizing. What science is being brought in the development of lightweight, advanced high-strength steel?
Okay. So I mentioned before, like advanced high-strength steels are quite sophisticated steels with their chemistries and with their complex microstructures. But these microstructures can be achieved with different thermomechanical processes and different heat treatment profiles. I mean, generally, when you say thermomechanical processes, people think that hot rolling and cold rolling. But instead of this, in addition to them, there are several ways to produce advanced high-strength steels. For example, there is a technique called deep drawing, especially for aluminum alloys and steels, especially high-strength steels. With deep drawing, for example, deep drawing is a thermomechanical process. With deep drawing, it is possible to achieve long and lightweight parts, for example, for car bodies. In addition to them, for example, there is a technique called hot stamping, also called hot forming. It is possible, quite novel technique, and it is used a lot nowadays to form complex geometries with advanced high-strength steels. The main idea to form, as you can understand from its name, is hot forming. So, for example, your steel is at high temperatures, and at that stage, they are trying to form it, and at the same time, they want to quench it to give a final microstructure. And this technique is quite novel, and it is quite popular to form complex geometries. So improvement in the thermomechanical processes helps us to form lightweight complex geometries for advanced high-strength steels and for automotive industry.
Adnan, what a great conversation we're having. In closing out this episode, is there anything that we didn't cover that you'd want to leave with the viewers?
I believe I cover like an advanced high-strength steel 101. It's a kind of introductory course. I believe I cover most of the things, but I can recommend the people who is watching this YouTube channel, if they are enthusiastic to study steels, for example, steel science is always open for improvements. For example, third generation advanced high-strength steels. I'm also planning to study quenching and partitioning steels, for example. Since they are still in RD stage, if they are enthusiastic to study, advanced high-strength steels are an excellent opportunity to study.
I would like to extend an opportunity, obviously, to come on with me again to talk about some of these other topics, because, even in those different topics, there's a lot to unpack and talk about. For the viewers of the episode, I will have the how to connect with Adnan on LinkedIn. This way exactly. You can connect with him and also join his community that he has in LinkedIn as well. Adnan, thank you so much for this opportunity to talk with you today.
Thank you for having me, Jim. It's an excellent opportunity for a master's student to talk about advanced high-strength steels in your YouTube channel. Thank you.
Hey, have a great day.
You too. Bye-bye.
So, Joe, for the lay person who's watching this episode who might only think that corrosion engineering